Alright guys, so today we're going to look at petrochemicals and in particular how they're used as a source of energy. And that source of energy really is just um, the stored products from photosynthesis, hence digging up sunshine. And then we're going to look at a process called cracking, which becomes fairly important as we proceed. And this is our dot point down here that we're covering. And let's move on. Okay, so what's the point? Basically, the point is to understand the natures of fossil fuels, so as a source of energy and their non-renewable nature. We want to define the term cracking as a chemical process. In other words, we want to understand chemically what's happening. We're going to look at catalytic and thermal cracking, and we're also going to explain cracking of petroleum fractions. Remember, that's the different parts that make up the mixture of petroleum to produce ethylene chemically. So we're going to talk about how that happens chemically. Now, we do need to understand one word, and that's free radical. So a free radical is an atom or a group of atoms, so a polyatomic ion that has at least one unpaired electron. This makes it unstable and highly reactive. Okay, so we're looking at an atom or group of atoms that have one unpaired electron and therefore highly reactive. And these can actually, if we talk about the way they can affect the human body, they can have some pretty disastrous effects. Alright, so energy from fossil fuels. Well, this is the world's major source of energy, is fossil fuels, whether we're talking about petroleum, natural gas, or coal. They're considered non-renewable resources. Now, long term, yeah, sure, they are renewable. Well, some of them are, but not in any time frame that's at all useful for humanity. So it really is the stored solar energy from photosynthesis, and here is the chemical equation for that, which we remember. Now, one thing we will notice is that it is the delta H, its enthalpy is positive, so it is a negative, so it's an endothermic reaction. Now, being an endothermic reaction, this means it stores energy, okay, so it absorbs the energy from the environment, and that energy is sunlight. The heat and pressure through sedimentation, they cause basically the sugar polymers to combine, and sugar monomers to combine, creating petroleum. So the petroleum itself is a mixture of about 300 hydrocarbons, and yes, it's most, smallish chains, but as we get further and further, we get trace amounts of very large ones. Okay. So natural gas. Natural gas itself is a mixture of smaller and more volatile. Remember, they're smaller hydrocarbons, so their melting point is a lot lower, and their boiling point is a lot lower, so their gas is easier. They're more volatile. So 75 to 90% of it, depending on where you go, is methane. 5 to 10 will be ethane. The ethane is not the useful one, remember that. And 3 to 6% will be propane or butane. And there'll be trace alkanes in there as well. All right. So, a few more definitions. Paraffins, naphthenes, and aromatics. Okay. So if we look over here at our little table here, we can see that all carbon compounds can be broken down or categorized into aromatic or aliphatic. And these aliphatics can be broken into alkanes, alkenes, and alkynes. All right. So, crude oil is made up of a mixture of these paraffins, naphthenes, and aromatics. So what are they? A paraffin is a saturated hydrocarbon. Saturated. That's alkanes. Okay, so single covalent bonds between all the neighboring carbon atoms. Straight or branched chains, it doesn't matter. Naphthenes are saturated ring-shaped molecules. Okay, cycloalkenes or cycloalkanes or cycloparaffins. Their boiling point is higher than the equivalent of the paraffin. So if you've got the paraffin hexane and the naphthene cyclohexane, the boiling point for cyclohexane will be higher. And then you've got the aromatics. The aromatics are molecules based on benzene, and they have double bonds in the ring. Okay, this is really important. So these are the three ways to draw it. And they're tasty, or they smell nice, and that's why they're called aromatics. Now, you'll notice that we've kind of ignored these. Okay, so These are what we call aliphatics. So you've got aromatic or aliphatic, all right? But the ones that we're concerned of the aliphatic hydrocarbons are paraffins or naphthenes. All right, and here's a little table to have a look at them. So we've got this is hexane, cyclohexane, benzene. They're all fairly similar. They're all fairly similarly related. Here we've got the branch chains of them. So you've got toluene down here. You can see that the aromatics have a slightly different naming system. All right. Now, hydrocarbon cracking. What is it? Well, basically, ethylene. It's one of the most useful substances. And remember, we talked about this in class. It's like the small Lego pieces versus the big Lego pieces. There's more you can do with the small Lego pieces. Okay, ethylene, because it's small, we can do a lot more with it, particularly with polymerization. So C2H4, so ethylene is ethene. It's one of the most useful substances we have in the petrochemical industry. It's in high demand, as it tends to be the source for most polymers, so plastics. Now, if you have a look over here, here's ethylene. We can see that it has a double bond. Okay, so we're getting something here. Sorry, that was just the bell. We've got a double bond here, and this is all singles, this is all singles. Okay, so how do we get there? Well, first off, cracking is the process of breaking large hydrocarbons into smaller molecules. And we can use heat or catalyst. We'll always use heat, but heat and catalyst or just heat. Naphtha. Now, this is your mix of various hydrocarbons. And these are what can be broken down into smaller hydrocarbons by cracking. So if we've got the naphtha, this is the mixture of hydrocarbons from usually liquid natural gas. Okay, so there are two types of cracking that we're going to talk about. There's thermolytic crack or thermal cracking and catalytic cracking, which will sometimes be called cat cracking. So why would we do it? Basically, the output of chemicals does not match the demand. Okay, so ethylene is super highly in demand, but ethane, which is the closest derivative to it, is in a really low percent. Like, it's a very small amount of crude oil. So cat cracking, let's get into it. Or actually, well, basically, here's what it looks like. So you get your pentane. This delta, that's energy. So that's when you put energy into it. So delta, so pentane, when you add energy to it, it causes essentially that bond there to break, and we now have a double bond here. Okay, so let's get into it. Okay, so catalytic cracking involves the heating of crude oil in the presence of a zeolite catalyst. Not always aluminium silicate, but usually aluminium silicate. That's the most common one. So in this process, it's carried out in a cat cracker, which looks like, well, I mean, for you guys, essentially it's safe to assume it looks like a fractional distillation tower. Long alkane molecules from, like, carbon 15 to carbon 25, they're broken into just two, an alkane and an alkene. And if we go back here, we see that happening. So you've got just as many hydrogens here, right? So this one separates, okay, and it loses an extra hydrogen, so that gives it 4 hydrogens there, to cap off the end over here, okay? So we do it using a catalyst, and this catalyst is, or tend to be, what we call zeolite crystals. Down here is the basic structure. Zeolites, usually, so commonly aluminium oxide or aluminium silicates, so silicon, oxygen, aluminium, with small amounts of metal ions attached. Generally, not always, there are other ways to do it. They're carried out at around 500 degrees Celsius with no air, because otherwise you'd have fire, with the pressure reasonably high. So they use less heat than thermal cracking, but it incompletely decomposes really large molecules into ethylene. So it's not as efficient. It's not as efficient, but it uses a lot less energy. So what are the advantages? Lower temperature, less energy. The catalysts are porous, so which means there's a lot of surface areas. It's not like a solid ball shape where nothing can get in. There's a lot of surface area, so you can have a lot of reaction happening at once. And they're reusable. Again, it's a catalyst. It doesn't take part in the reaction. It shouldn't change. It has a very high thermal stability, so you can heat it up and it's not going to break apart. All right. So where do we use zeolites? This is just mostly for your interest. It's not so much for this, but we use them all over the place. EPAs, okay, so we use them as a way to speed up decontamination of water and to get out heavy metals. It's using in construction, in agriculture, petrochemistry, obviously, gas treatment, and medicine. So thermal cracking. All right. So since catalytic cracking alone is not efficient enough to meet the demand for either propylene or ethylene, we use hydrocarbon. We use thermal cracking as well. So it's thermal or steam cracking. We're going to call it thermal cracking. Now they're mixed with steam, really, really hot steam, and they pass through pipes between 750 to 1,000 degrees Celsius. I think your textbook says that about 850. So it's just above atmospheric pressure, and it involves 3 processes. But remember, it's a closed system. Okay, first you have initiation. So this is when the alkane is pumped into the steam cracker. Okay, so it's mixed and heated up for short periods of time, which causes it to split into 2 radicals. Okay, since they're radicals, they're highly reactive. Now, the free radicals decompose further in the phase called propagation to produce even smaller free radicals, and this is because they've continued to be heated, and so they break apart smaller and smaller. Termination. So the hydrocarbon is placed into a quench tower, so really, really low temperature, and this prevents further cracking. So while we're doing this, the free radicals combine to form stable compounds, and then they're recycled for further cracking. So what happens over here, right? So this is decane, it's heated up, you get 2 pentanes, all right? So the pentanes then break further down, they crack further, and you have a free radical over here of propane, and you've got ethene or ethylene. And this ethylene, it only has the 2 hydrogens, the 2 hydrogens per carbon, and that makes it a stable ethylene. Then we cool it down very, very fast through termination. The propanes bond together rapidly, and we pull those out, recycle them through fractional distillation, and we reheat those ones up. All right, so that's thermal cracking. You might want to break that down and go through it a couple more times and try and find a simple way to put that out there. Here's a diagram. So we get decanes here. It gets heated up in initiation, and it breaks into these 2 here. Along the middle, there's your 2, what are they called? Free radicals. So then we go through propagation, it's heated a bit further, and we get these ones here. Okay, so we get these ones, and these ones come separate. So these ones stabilize because they form a double bond, whereas these ones here, they're still radicals. At termination, we cool them down rapidly. These guys join together, and we fractionally distillate the ethylene out. That was simpler. I don't know why I didn't just say it like that in the first place. All right, that's it. That was a long one. I'm very sorry. Good luck.